For this video, we're doing a quick review of 5.2, which is circuits. So have your data booklet out, a notebook, and a calculator, and of course something to write with. Actually, you don't need the calculator. Okay, so on page 3 of the data booklet, these are the electric circuit symbols. The cell, battery, AC supply, switch, voltmeter, ammeter, resistor, variable resistor, a lamp or a bulb, potentiometer. We did potential divider circuits last year. Light dependent resistors, we saw some of these. We haven't worked with thermistors. This year we'll get to transformers, won't do heating elements, but we've worked with diodes and we will work with capacitors. So these are the schematics you use when you draw your circuits. And then of course on page 6, of the data booklet, we have these equations. First set are Kirchhoff's circuit laws, which state that the sum of the voltage in a loop around the circuit should equal 0. The sum of the current into or out of a junction in the circuit is equal to 0. So the current going into a junction needs to equal the current going out. This is Ohm's law, resistance, which has units of ohms, equals V over I. Voltage or potential divided by current. The symbol for current is I. It has units of amps. Power equals V times I. Power also equals I squared times R. Power equals V squared over R. The total resistance for resistors in series, you just simply add up those resistances, and that equals the total resistance in the circuit. And if you have resistors in parallel, 1 over R total is equal to 1 over R1 plus 1 over R2 plus etc. And then this last equation, remember, this is the resistivity value, this rho symbol. It looks like a lowercase p, but it's not. Greek letter rho is equal to R, resistance, times the cross-sectional area A of the resistor divided by the length of the resistor. Okay, so remember we have this circuit here. This is a series circuit. I have 1, 2, 3 resistors, and they're wired in series to the battery. And if we remember, current is always drawn going out of the positive terminal. The positive end is long. It goes around and into the negative terminal. So what you see are 3 resistors, and they act like a hurdle, if you will, for the current. The current in this case is represented by the red arrows. If I reduce the resistance by taking out some resistors, what you'll see is the current flows faster. When you have more resistors in a line, current flows slower. When you have more resistors in a line, the battery will take a longer amount of time to drain. Okay, these are all 3 identical resistors. Now the battery supplies energy to the circuit, if we remember. So what'll happen, if I only have 1 resistor in the circuit, all of that energy, really the potential, the joules per coulomb, that's energy per unit charge supplied by the battery, will be dissipated by the resistor. So if I have a 9-volt battery, that's 9 joules per charged particle being supplied. That's a push, a drive for these red arrows representing the electrons. Then the resistor is going to use up 9 volts. There will be a potential drop of 9 volts, 9 joules per coulomb for the electrons traveling through this resistor, and then the electrons will travel back to the other end of the battery. If I add another resistor in series, what happens is I have less flow of electrons, so there's less current. And now the voltage dissipated by each resistor needs to add up to the voltage of the battery. So the battery has 9 volts, and if I have 2 identical resistors in series, then this resistor will consume 4.5 volts, or will use up 4.5 volts, and there will be a potential drop across this resistor of 4.5 volts. 4.5 plus 4.5 equals 9. These are 10 ohm resistors. So that means the total resistance in this circuit is now 20 ohms. Let me add one more resistor here. Okay, you can see the current goes even slower. Now what would the voltage be? How much voltage is dropped across each resistor? Well, it should be 3 volts. 3 volts here, 3 volts here. So the sum of the voltage drops in series for these resistors is equal to the voltage supplied by the battery. Now what is the current in the circuit? I can use Ohm's law. V equals I times R. So I'm looking in my data booklet. I see resistance is equal to voltage, the voltage supplied by the battery, the voltage dropped across a resistor. But if I'm looking for the total current, I need to use the total resistance is equal to the total voltage divided by the current. If I want current, which I'm going to try to calculate here, I is equal to V over R. I equals V over R. So I have my calculator. I'm going to do 9 volts divided by the total resistance in the circuit. These are series resistors, so I'm going to add them up. 10 plus 10 plus 10 is 30. So 9 divided by 30 should give me the current, and I get 0.3 amps. I'm going to measure that just to make sure I've done right. 0.3 amps. Now, what if we have these are resistors in parallel. Let me show the current. The current is traveling really fast out of the battery, slower through each of the branches. When current gets to a node, this current will split. Some of the current travels along this branch. Some of the current keeps going, traveling along this branch. Some of it will keep going and travel through this branch. But with these 3 resistors in parallel, they are each pulling independently from the battery. This puts more demand on the battery. The battery is going to run out faster like this. Each resistor in parallel has the same voltage as the battery. You should see 9 volts. So what is the total current then going to be? I can get the total current by calculating the total resistance. These are in parallel. So I will do 1 over 10 plus 1 over 10 plus 1 over 10. This gives me 0.3 inverse ohms. Now, if we have 0.3 and I want the total resistance in the circuit, you raise this number to the -1, and the total resistance in this circuit is 3.33 repeating. It's way less resistance in the circuit, and notice all the current flows in here. So let me cut this. Let's measure the current and make sure we get 3.33 amps right next to the battery. 2.70 amps right next to the battery. Let's see what happened. Oh yeah, I didn't do 9 divided by that. Sorry, 9 divided by 3.33 repeating is 2.7 amps. Total current, total resistance is 3.33, and the current is 9 volts divided by 3.33 total ohms for 2.7 amps. Sorry about that confusion. As you can see, if we're in parallel, the battery is going to run out much faster, and each of the resistors gets the same voltage as the battery itself. Okay, now what about for a combination circuit? When you have combination circuits like this, here I have 2 resistors that are in parallel, and then they themselves, this parallel connection is in series with the resistor that's in series with the battery. So let's see how current flows. Current flows out of the positive end of the battery, because this is conventional, through the resistor, and then the current has to split at this junction. All of these resistors are identical, so let's see if we can calculate the correct value for the current before we measure. First thing we do is we combine these 2 resistors. They're in parallel, So I'm going to get an equivalent resistance. 1 over 10 plus 1 over 10, that's 0.2. And then if I invert that number, raising it to the -1, this is the exact same as having a 5 ohm resistor. The same as having a 5 ohm resistor. Now this 5 ohm equivalent resistor is in series with a 10 ohm resistor, so the total ohms in the circuit are 10 plus 5, that's 15. So the total current in the circuit, the total current flowing through this 10 ohm resistor should be equal to 9 volts divided by 15 ohms, divided by the total resistance in the circuit. So if I do 9 over 15, this gives me a current of 0.6 amps. All of this current flows through this 10 ohm resistor, and it splits half and half through this 10 ohm resistor, through each of these 10 ohm resistors. So I expect 0.6 to measure 0.6 amps of current here, to measure 0.3 amps of current through either of these branches where they split. So let's see if we measure that. I'm going to cut the circuit open, add an ammeter here. I get 0.6 amps of current. I'm going to cut it here, add an ammeter here. I should see 0.3 amps. Yes, because it's split. I should see the exact same 0.3 amps here. And this is how circuits work. And this is a video in case you have forgotten how these work. The next video I show will be how to calculate, how to solve the problems that you are tasked with solving. But the link to this simulation will be in the One Notebook, and it'll be on the hub. So make sure if you've forgotten, play around with these circuits. And thank you for watching.